Welcome back to the Deep Dive. Today we are tackling a really fundamental paradox, something you might not even realize is a paradox.
It's one of those things that's just hiding in plain sight.
Exactly. It's this. Why can your brain achieve absolute 100% certainty, what we're going to call P1 in an instant, but our most advanced digital systems, AI, huge databases, they can only ever get close?
They can only ever reach a high probability. Maybe P equals 0.99 if they're lucky.
And that tiny gap, that 1% difference between knowing and just having a really good guess.
That gap is everything. It's the difference between knowing and calculating a high likelihood of knowing. And it's one of the single greatest sources of hidden waste in all of modern technology.
We're talking trillions of dollars annually.
Yeah.
So our mission in this deep dive is to unpack this architecture of certainty, this concept called SEPIAC.
That's structure equals physics equals hardware. And we're going to pinpoint the exact moment a decision made 54 years ago that basically put a splinter in the digital mind.
Okay, so let's unpack that. SEPE, to get our heads around it, let's start with some real-world examples. We all experience this P1 certainty all the time.
Constantly. It's the default state for a biological system.
Right, like you walk into your kitchen and the smell of coffee hits you. You don't run a statistical model in your head thinking, there's an 87% chance that's roasted Arabica beans.
No, you just know it's coffee. Instantly. Zero synthesis delay.
Or you hear a chord in a song and you just feel it. It's a feeling of recognition before you can even name the notes. How is the body doing that? How is it bypassing probability?
It's because the body is built on SEPE. That moment of recognition happens because the memory isn't just, a piece of data stored at an address. The semantic properties, the structure, the meaning are physically co-located.
With the physics.
With the physics in the same neural substrate. The hardware.
So meaning and location are literally the same thing. They're unified.
Precisely. That's the whole principle behind Hebbian wiring. Neurons that fire together, wire together. When the structure of your data is identical to its physical geometry in the brain, well, verification is instantaneous.
You don't have to go looking for it.
You don't have to chase pointers across a network to assemble the meaning. The knowing is the physical experience of the substrate catching itself being right. It's a collision.
And the sources bring up this incredible efficiency advantage. They call it the thermodynamics of sapiens. A computer has to process what's called Shannon entropy.
Right, which is just a measure of all the randomness and statistical noise in a set of data. And for a complex recognition pattern, the number cited is about 65 bits of entropy.
That's a lot to process for one moment of recognition.
It is, for a sequential machine that has to chew through all that noise. But the grounded brain, because structure and physics are one, it skips the fluff. It recognizes the pattern holographically using something called compressed Kolmogorov complexity.
So instead of 65 bits of random data,
it processes maybe 1 bit, the essential structure. That's it.
that is a staggering difference. That's a 65 times amplification factor.
It is, and that's why evolution paid for consciousness. It wasn't a luxury item, it was a thermodynamic imperative. Grounded prediction is just physically and energetically cheaper than running probabilistic checks on scattered data all day long.
The animal that can build its next move on a pivot foundation.
It saves a huge amount of metabolic energy compared to the one that's constantly recalculating the probability of the ground being there.
So what's stopping a machine from achieving that? Why can't we solve that 65x problem digitally?
Because our digital machines, by their very design, start from the opposite assumption. They assume that a memory address is just an arbitrary bucket, totally separate from the meaning of what's inside it.
We have to use software to bridge that gap.
We use algorithms and probability to try and guess the essential structure from all the scattered pieces. And that's inherently expensive and, probabilistic. It throws you right back into that high entropy verification loop.
You can really feel this difference. I love the analogy in the source about reaching for your keys. You know you left them on the counter. Your fingers close on empty air. You don't sit there and deliberate, is this 87% empty space?
No, there's no calculation needed. Your system, your hand, your arm, it instantly registers the absence of collision, the wrongness.
That visceral instant feedback.
That is what digital systems are structurally prevented from experiencing. They can only ever report probabilities based on what the software thinks should be there.
Which brings us to the crime scene, I guess. The structural violation itself. If our bodies do this naturally, where did we go wrong in computing?
We can pinpoint it to a very specific moment. 1970, the antagonist, and this is the ironic part, is one of the most brilliant innovations in computer science.
Edgar Codds' paper on normalization.
The bedrock of the relational database, absolutely. Codds' genius idea was to separate the meaning of the data, the relationships, from the physical storage.
So he took the soul out of the body, basically.
That's a great way to put it. He proposed scattering semantically related data across all these different tables and then using pointers, what we call JINs, to reconstruct the relationships only when you needed them.
Okay, that sounds horribly inefficient based on everything we've just said. Why would he ever do that?
Because of the economics of 1970, storage was unbelievably expensive. We're talking $1,000 for a single megabyte.
$1,000. Wow.
So redundancy was the mortal enemy. Codds normalization was a beautiful, elegant solution designed to eliminate redundancy and save physical space. It was perfect for those inverted economic constraints.
But today, that's completely flipped on its head. Storage is basically free.
And verification and complexity are the things that are ruinously expensive.
Yeah.
But we are still to this day following structural advice that was optimized for a world that no longer exists.
And the result is what the sources call drift.
The result is the distance Codd created. That separation forces every single query to constantly bridge the gap between meaning and location. And bridging that gap costs energy, it dissipates as entropy, and it accumulates as drift.
So drift isn't just a bug, it's the physical cost you pay for having the wrong geometry.
It's the systemic loss of cohesion.
Hmm.
The sources measure it somewhere in the metal 0.2% to 2% range across most big digital systems, and it adds up. Roughly 0.3% with every single probabilistic decision.
And when you scale that up across the entire global digital infrastructure, that's the trillion-dollar hidden inefficiency.
It is the cloud tax. It's the $1 to $4 trillion a year in wasted compute and failed projects, and honestly, the human cost. Think of the engineer page at 3 a.m. trying to fix a production outage.
Because a 47-table Joyanne failed.
Exactly. They're not fixing a bug in the code. They are trying to manually bridge a geometric gap that should never have been designed into the system in the first place.
You're not fixing software, you're fixing broken geometry. That's a powerful way to frame it. And we see the consequences, the screams of this broken substrate everywhere. Let's start with the Air Canada chatbot.
A textbook case of grounding failure. The chatbot just hallucinated a bereavement fair policy and made it up.
But it sounded so confident.
Of course it did. Because the actual knowledge, the real terms and conditions, it existed somewhere in a PDF, but that truth wasn't tied to a verifiable coordinate. So the AI, which runs on probability, it just optimized for plausible syntax. It gave a grammatically perfect, confident-sounding answer.
You couldn't check if it was true.
It was structurally incapable of saying P1, I know this is true, or P1, I know this is false. It could only report P equals 0.99. This looks about right.
And that structural gap enables hallucination. It also opens up huge security holes.
Look at the Capital One breach in 2019. That happened because of one misconfigured firewall. The policies, the semantic rules, they existed on paper. They were signed off, but they had drifted from the physical geometry of the infrastructure.
The map no longer matched the territory.
Exactly. We treat security like a checklist, like rules to be read, not as a physical geometry that must exist and be enforced in the substrate. Attackers just walk right through that gap.
And this is only getting scarier as we move into the age of AI agents. The same systems that were just hallucinating refund policies are now.
Now they're taking actions, they're transferring money, they're changing system permissions.
Which is terrifying.
It's exponentially riskier. Something like 90% of early AI agents fail basic security tests. Why? Because the substrate can't verify its own outputs. If the agent can't be certain that its intended action is grounded in reality, well, letting it loose is a recipe for catastrophic failure.
This makes the pop culture analogy in the source material, the comparison to Agent Smith from The Matrix, just so perfect.
It really is a perfect metaphor. Agent Smith is the normalized database, the purely computational mind. To him, things like love or purpose, things that are grounded in a physical, emotional substrate.
He calls them vagaries of perception.
Because to his system, which lacks, say, Pat, that's all they are, just ungrounded data points floating in vector space. He can calculate the probability that a human will choose to rebel.
But he can never land on the actual decision itself.
Never. His system can only get to P 0.99 likelihood. But Neo's certainty, his P1, it comes when he makes a physical choice. Because I choose to, and that choice is instantly grounded in the act of his body standing up.
It's a physical collision. A coordinate.
A non-probabilistic coordinate that the matrix's architecture simply cannot touch or compute its way out of.
So if the problem is this dissociation, this gap, then the solution has to be grounding. How do we bring SAP back into silicon?
By fundamentally changing the geometry of our hardware and our software, we have to reclaim the body's architecture.
Mm.
And SAPI isn't really a brand new idea. It's more of a recoding of existing concepts that are all trying to do the same thing.
Okay, so walk us through some of those. What concepts does CP unify?
Well, first, it's pretty much the definition of neuromorphic computing. You see companies like Intel with their Lowy heat chip. They are trying to physically eliminate the von Neumann bottleneck.
That's the gap between the memory and the processor.
Exactly. They co-locate those functions, forcing the hardware to act more like a biological neuron. The structure and the processing become one.
So we're moving the computation to the data instead of constantly moving data to the computation.
That's it. Second, it directly solves the old symbol grounding problem. Digital systems usually just know that the word apple statistically appears near red or pie. Sate forces a physical connection. The system can understand chair not just by its context, but by its physical geometry and its relationship to a body.
And the third concept, semantic locality.
That's the key. It means ensuring that data points that are semantic neighbors, things that belong together conceptually, are also physical neighbors in the hardware. It's the direct reversal of Codds dissociation.
So when you ask a question, the answer is already there, altogether.
It's already co-located. You avoid those insane 47-table joyens and all the drift they cause.
But that claim, P1, it always brings up philosophical questions. I mean, my brain can be absolutely certain that a dream is real, but it's objectively wrong. So is that kind of certainty still useful?
That is a crucial distinction. A SAPA certainty isn't about guaranteeing objective truth. It's about guaranteeing traction and decisiveness within the system's own boundaries.
So it's about ending the debate.
It is. That instant hit of P1, whether it's your hand hitting a real door handle or your brain feeling a phantom limb, it serves as what's called a deterministic halting condition.
A halting condition. It stops the verification loop.
Correct. It puts a cap on the energy cost. It stops the endless cycle of guessing. Evolution paid that massive 20% metabolic price for the human brain, not for philosophical luxury, but for the ability to break causality and act.
The organism that treats a rustle in the grass as a P1 threat, even if it's wrong sometimes.
That's the one that survives. The one that waits to calculate an 87% probability of tiger gets eaten.
So you're trading the possibility of infinite expensive precision for guaranteed cheap and instant decision-making.
And that gets us to what we call the freedom inversion. We think freedom is about having infinite options, but that's just drift. A car spinning its wheels on ice has total freedom of movement.
But zero agency, zero traction.
Exactly. Constraint isn't a leash. Constraint, that structural P1 certainty, is the asphalt.
So you constrain the substrate to get P1, and that frees the agent to act decisively. Grounding gives the system the traction it needs.
You get to eliminate the anxiety of never fully trusting your own outputs. You can finally stop worrying about verifying the floor and actually start building the house.
This has been an incredibly clarifying deep dive. I mean, the core takeaway here is that our biggest digital problems, hallucinations, security gaps, this trillion-dollar waste, it's not a lack of compute power.
It's not about bad training data either.
It's a structural violation. It goes all the way back to Codds' 1970 paper, and we're still paying the price for it, even though the economics that justified it are completely gone.
And once you have this knowledge, you can spot the dissociation immediately. The next time you see a system design with a 12-table join, you'll feel it. You'll feel the broken geometry.
You'll know that the drift, the energy loss, is baked in. It's guaranteed.
Right. It's about fixing the floor so we can build reliable things without constantly worrying about them collapsing.
Which leaves you with a final, provocative thought to mull over.
If all the systems you build, all the systems you're responsible for, could achieve that structural certainty, that P1 traction and decisiveness, what truly complex, fantastic, and currently impossible digital structures would you finally be free to build on that solid, grounded foundation?
A great way to end it. Thank you for joining us on The Deep Dive. We'll see you next time.